Alrighty. Well, happy Thursday again. So we started with stacks, queues, and Deques, right? Deques are fun, kind of the combination of the two, and looked at performance of these. Right? Most of the time, what we're looking at, right, is how fast it takes to do things. That's our time complexity. So pull up PyCharm here, and we got these things relatively fast, right? The stack was good already. It's pretty good on average. Best case. The worst case, we still ran into those problems where we had to double our array for storage. We know that was fine. With our queue, right, initially it started off not so great, right, because the way that we were adding things and then having to resize our arrays and taking things away, we ran into some trouble with shifting everything down when you wanted to remove an item. We said, well, that's not great. We don't get good performance out of that. And then we talked about this idea of the circular queue, that we can do better by not having to shift everything down. Right? So when we talk about our performance for circular queues, we got to much better, right? NQ on average was great. Fantastic. Sorry, let me zoom in a little bit more. Average times fantastic, just like adding to an array. Right? On average is fast. We know it does have to double eventually here, but DQ, we got better. This is the problem we had before with the original queue version here, but now we're still doing great, because when you DQ something, we just leave it an empty space, and now we're tracking where the next open one was. So we were able to increase our performance by trading off some memory usage. Right? We said, hey, we're just going to leave a gap here. We have a gap. That's okay, and we'll figure out eventually maybe that gap will get filled back in here. Getting the thing out the front was really easy. So we can do even better than this, though. So when we look at these worst case times for stacks and queues, we can improve them by using a different model. So this is where things start to get a little crazy. So next week we're going to get into linked lists, where lists you can get things by index and you can do things all by index. But we're going to start this idea of linked objects today to look at stacks, queues, and Deques and how we can make them perform better. And that's sort of the goal here. And what we're going to trade, we're going to see, is a little bit of that space complexity, that idea of how much memory am I using. We're going to end up using a little bit more memory, but the trade-off is things will happen faster. So we're going to get better time complexity with that trade-off. And for most of what we're doing, right, our computers have ridiculous amounts of memory, right, gigabytes of memory. So depending on how much stuff we're working with, that's a pretty good trade-off. Now, if we're working with like billions of items here, and now we have to double the amount of memory we're using, yeah, maybe we've done a bad thing here. And that's why we want to look at all these data structures and think about how they perform, because that helps us choose the right one we're going to use for solving our problems. And that's all the goal here, is we're learning how to design solutions efficiently here. So let me go, we're still in week 5 here. I'll add another class in here. Let me just add another Python file here. This is our better stack. Okay, so we're going to start with stack here. This is, and we'll just call this one a linked stack. This is probably easy. So our linked stack, we create a stack, right, and we can start adding things to it. So we still have the same methods here. So we'll come back and fill in a init. We're going to have push, right? You push an item on the stack, you pop an item off the stack, and you peek, right? You look at what's on top of the stack here. So for now, I'm just going to return none just to have these filled out here. We can come back and add all these in later. This way it won't yell at us at least. So push. If you're not returning anything, you just say pass, and at least Python will be happy with that. So what we need to do with the linked stack is we need to store things differently. We're going to move away from using that array, that fixed, here's some contiguous block of memory, array worth of storage, and we're going to have nodes. Now, node is a really funny concept here, so this one is definitely worth drawing. I forgot to grab my tablet. I almost packed it. I was like, no, I don't need it today, and that was really wrong. So the idea with a node is it has two things. It has the item, and then the next thing that it knows about is what comes next, the next node. And what we do is we build multiple nodes in memory. So when I want to add something, I'm going to create a node and say, okay, this is where the item is. And remember, what we're actually storing is just a memory address, right? X2379 somewhere. We're not actually storing the value here. We're storing a reference to something somewhere else in memory. But it says here's where that thing lives. Then the next, Now it might be none, right? If there is no other item, we can be none. There is nothing that comes after me. But if I want to add another item, what we do is we build another node here. We add the item, and we add the next. So I'm going to stop typing all the things out or drawing all the things. So I for item, N for next. And then this is no longer none. What happens is it says, where does this node live in memory? It's essentially pointing at where this node lives in memory. What's great about this is I don't need a contiguous block of memory. Python just says, hey, operating system, give me some memory. We don't care where it is. Remember, getting stuff out of memory is as fast as it gets. I don't get anything faster than that. So to add an item, it's just going to say, okay, put it somewhere, and then now I know where to go look for it. So if I want to add another item to my stack here, we're going to make a new node. Here's an item, here's a next. Again, this next was probably none. Sometimes you might use a slash for none or put in none. So if there is nothing after, it's none. When I go add a new thing, great, now this one will point to here. It is no longer none. It has a next, and I have an item. And we can keep on doing this. The worst case time is still constant time because it's still the same number of operations, regardless if I have 5 items in my stack or if I have 5,000 items in the stack. Nothing happens to the existing items. All we do is change the next pointer here. We say, hey, the next value now, there's something that comes after you. So this works very, very, very fast. So even in worst case performance, we get constant time. If our worst case is constant time, our average is obviously going to be constant time, and our best will be constant time. So we don't even need to do that amortized average and say, well, on average, if you look at all of these, some will be slow, some will be fast, but it's constant on average. It is constant no matter what, even on our worst case. So by using nodes, we're using more memory, right? Because now I have a node stored in memory. The node knows where the actual value is stored in memory, and then the node needs to know where the next node is. So we're trading off some of that memory use space, that space complexity. We're going to use more memory here to make this thing faster. And, for a lot of cases, this is a really good trade-off. We're not doing anything at billion times scale. So for our purposes, this is a good trade-off. Once we get to those larger scale things, now we need to start worrying about which one is actually better here. So to do this, we can build another class. So you can actually have a class inside of a class. It's really weird in Python, but it's okay. So we're going to have a class for node here inside. And then for node, then it needs to know 2 things. It has the item and it has the next. Now we're going to say next, we're going to default this to none. So if you don't tell me what comes next, I'm going to assume there is nothing that's next. And that's that pointer to where's the next node here. Okay. And then we just set self item is the item and self next is the next. That's all it is. We'll go grab these things. And this is an internal class. The idea is someone using the linked stack doesn't need to know about node. It's not going to be publicly accessible here. We could mark it as private and do some of those things. It should be okay. No one's going to go try and go get at this here. So we'll just say, hey, this is mine. I don't need to mark these things as private and have public functions to get at them because no one else is going to be using them. I'm not giving anyone nodes. I'm only using it internally. So we're not going to worry about trying to hide any of these values and say, hey, they should be private or what here. Let's worry about next. That should be okay. I don't think should be fine with next. And that's all node is. That's all we're going to do with it. So when we init, when we create our linked stack then, right, what we need to start with is where is the top of my stack? Right? The stack knows what's on top. And when you add something, you add it on top. When you add something, you add it on top. When you add something, you add it on top. When you pop, you take the top thing and we go back. So all we need to be doing is following this chain here. So right now, self top is none. We don't have a top. There's nothing here. Eventually, we're going to start adding nodes. We can add nodes, we can add nodes, we can add nodes, we can add nodes. So to peek here, we're going to first see if something exists because bad stuff could happen if I don't have top, right? Because ideally, peeking is to say, hey, what's the item referenced by the top node? But if there is no top, we're going to have a problem here. So we can check real quick and say, hey, if self.top is null or is none, then maybe we raise an exception. I don't know. I think there's like an empty one here. The value error is fine. And we can say, hey, stack is empty. To let the caller know, I can't, you can't. It's not here. There's nothing here. If that doesn't happen, then we're just going to return self.top.item. Here's the item that the top node knows about. Right? We've got that. Okay, let's do push next. This one's a little easier to handle first. So when you add something to the stack, right? I have my arrows a little bit backwards here because you could know what comes next, but to add something to the stack is going to be a little trickier. So what we want to do is we want the top node to know what comes after it, what's underneath it. And then we want this node to know what's underneath it here. Because this way we can follow this. When I take the top off, then I know what comes before it. I'm sorry, when I take the top one off, I know what's under it. And when I take that new top off, I know what's under it. When I take the new top off, I know what's under it. So we can follow this chain of, hey, what comes after you, what comes after you, what comes after you, or what's underneath you, as we're thinking of this as a stack here. So when I push something, I'm going to make a new node here, right? So this will be the new node equals self.node. The syntax for this is a little funny because node is an inner class. It technically it's part of self, right? It is a linked stack.node. You'll get used to the syntax. It's just a little funky here. We're going to make a node, and we have to give it the things that init wants. So we need to give it the item. So sure, we just pass item right through. You told me this is the item to push on. I'm going to give it here. And then what comes next, right? Well, what is going to be underneath the new top is going to be self.top, the old top, right? What currently is the top thing is now what comes after the new top, right? So if we think about, let's actually like pretend to add some items here. So let me just erase some of this stuff here. We can draw it all out. So throw out some numbers. Well, let's do numbers because those are easy. So we're empty right now. So our top here is none. There is no top. Doesn't exist. So this one is none, right? So when we go add a new value, what number should we add? 5. So we're going to make a node. We're going to say, hey, our value here is 5. And again, this will point to somewhere out in memory, but this is easier to write here. And then what comes after 5 is none. There is no top currently. Now, top needs to become the new thing. So now self.top equals new node, right? So now I have a new thing that's on top. If I do this again, let's add another value, right? So top is no longer none, right? So we can erase this one here. Top isn't none. And then this next here is none because it was the top, right? What value do I want to add next? 7. All right. Oops. Let me go back and erase this one here. Getting too close up to the top. All right. So we're going to add 7. So we make a new node. Its value is 7. That's the item it's storing. Its next value then is the current top. Well, the current top is this one, right? Then we say, okay, hey, top, you're no longer here. We have a new top. You're now the top of my stack, right? And we just continue on, continue on, continue on, continue on. And every time we push something on our stack, right, it's a constant time operation. We make the node, and then we change top, regardless if we have 5 items or 5,000 items. So we get constant time performance, best case, worst case, average case, which is fantastic. So this is super fast all the time. Right? And we just keep on adding and adding and adding as far as we want to go. So now popping something off, right? Again, we should check and make sure, hey, if we're empty or not, we should probably raise an error here. And now I have the same code twice. I feel bad about myself, right? So I'm going to just refactor this real quick. So let's refactor, and we can introduce this as we're going to extract it as a method here. Let's call this check for empty. And this will only be private, right? So we mark this as a private method here. And say yes. Yes, replace. So it found that we already did this here, which is super handy. Like this PyCharm is just fantastic. So now I can check for empty, right? And we're checking for empty. We don't have the same code twice. We feel better about ourselves. So we'll check for empty. If we raise the exception, stops going anyway, we're good. Other than that, then, if I want to pop that item off, so I need to get the item first, because I'm going to return that in a minute, but I don't want to just return it right away, right? When you pop, it has to come off. You have to remove it here. So I'm going to say, hey, the item is self.top.item, right? Give me the item that's on top. Then what needs to happen is now I need to change top, right? If I'm going to pop the 7 off here, this one needs to go away, and the new top becomes whatever this one said is underneath it, right? So then self.top is going to become self.top.next. The syntax here looks really crazy. It's okay. So we're saying the new top is old top's next. or underneath, really, right? If we're thinking about this in terms of, usually we think of stacks as like putting things on top of each other because that just works out well in English, right? Here's the next. So we pop it off. Now we have a new top. Great. Now, if nothing references this, right? If we change our top, we say, hey, you're no longer the top here. This is the new top. This is going to go get garbage collected, right? It's no longer referenced by anything, so Python can go and free up that memory. That happens behind the scenes. We don't have to do anything special for that. In other languages, you have to do all sorts of special stuff, which is why I love Python, right? And we just keep on going. So if we only have the 5 left, we say, okay, let's pop off the 5. Sure, let's grab the 5. Let's make the top the thing that is next. So top now is none. That's okay. Top can be none. That's an okay. That's a valid state. We're an empty stack if our top is none, right? That's where we started with when top was none. That's okay. It just puts us back in that state. Top no longer points to 5. We're good. So the last thing we do then, right, is we return item. Return item, right? Grab the item, change your top, because we need to make sure we have this before we change top, because otherwise we're going to lose it, right? And then we can return it. Well, that's it. This is our linked stack. So performance-wise, right, for popping here, average case O of 1, constant, worst O of 1. Right, same for peak. I mean, peak was already fast, right, with the other one here. The push, worst case O of 1. Remember, with our previous array-based or list-based stack, that worst case was O of n because we had to do that resizing. We had to say, oh, there's not room in my array. I need to cut, or my list. I need to make a bigger list and throw these things in here, right? And Python did that behind the scenes for us. If we just use the list, it would resize. But we graphed that out. We saw, yeah, you see those spikes every now and then when it has to resize, right? But now we have fantastic performance at the trade-off of a little bit more memory, which is not a bad trade most of the time. This one works out nice. So that's our linked stack here. Let's make a, I should just call that linked, right? Instead of better, let me rename that. So refactor, rename. We'll call this our linked stack. And we're going to do the same thing with a queue, right? So we'll make a linked queue here. Class for linked queue. Now it uses the exact same internal node here, which is fantastic. Got our node. Now with the queue though, things are a little trickier, right? Because with the queue, you take from the front and you add to the back. So I need to know where the front is to take from it, and I need to know where the back is to add to it, right? So when we make a queue, we need to know where the front and back are. We need to track those separately. So we can say, hey, when we init, there we go, init a queue, we're going to have self.front is none to start, and self.back is none to start. Right? Where's the front of the queue? Where's the back of the queue? Well, we're empty. We don't have one right now. And with queue, right, you enqueue, you dequeue, and you front, kind of like peak, you just call it front. What's the thing at the front here? So we can say, hey, give me the front value. I'm just going to return none for now. We'll come back to that. When you enqueue an item, right, we want to add here. Again, I'm just going to return, this one's pass, so we don't return any values. And you dequeue, I'm going to return none to start. Okay, so we've got our functions that we use with our queue. So this one is a little bit trickier because we have to track front and back. We have a couple more edge cases that cause us a little bit of trouble here. It's okay, it's workable. We can make this work for ourselves, but it's going to take a little extra work. So to get the front, again, we can check for empty. This one's pretty easy. I'll just steal this check for empty here, but it's not front anymore. We can say, hey, if self.front is none, we'll return queue is empty. Raise that value or say, hey, the queue's empty. Right? Bad stuff happened. So to get the front, first we check self.check for empty. If we're not empty, okay, now I can give you a front. So I'll return self.front.item. What's the item referenced by the front node? Right? I'll show you what it is. Again, we're not removing anything. We're just giving you access here. And that one runs constant time, just like it did with the list-based one. Right? Just looking at something is really fast. No worries here. Now, enqueue and dequeue get harder. So to enqueue something, we have two cases. Right? The first case is we're empty. The second case is we're not empty. So if we're empty, the first node actually becomes the front and the back. Right? If you only have one thing, you are the front and you're the back. So it's a little bit funny here for tracking this. Well, we need to check that. We say, hey, if self.front is none, then self.front will be a new node. So we can say self.front equals self.node given the item. And then what comes next here is just none. There is nothing else. Right? We don't need to set a next here. That's pretty easy because we had nothing there. But then now that we have a front, we also have a back. So self.back equals self.front. Right? Now back and front points to the exact same node. So if we're drawing this out in the picture here, go down a new page here or something. We have a node, right? It has the value 3 or something. We have front is this one, and we have back is this one. So front and back point to the same thing. It doesn't have next because there's nothing next, right? So to add to the queue, if we're not empty, we are creating a new back, right? So the current back gets a new something that comes after it. So if we want to add the number 5, we're going to make a new node, right? 5. It's the end, so it has none. Its next is none, but the current back needs to say, hey, now you have a new thing that comes after you. It's this one, by the way. Here it is, right? So we're no longer none here. And then back, you don't point to that one anymore. You point to the new back, right? And same thing if we want to add another node. All right, add another node in here. So, sorry, I didn't center this very well here, but we'll add another node here. Some number here. This one now points here, and then back points to that one. And we're just adding, so it's essentially like a chain, this linked idea. We're all linked together in a chain. I'm in front, you come after me, 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 right? Like at the grocery store. If you want to get in line in the queue, you get in line. You're the new back of the queue, right? Someone else walks up, they try and cut in front of you. You say, no, I'm the back of the queue. You got to get behind me. They're like, oh, okay, sure, I'll get behind you, right? And they get in the back. Then they're the new back. Eventually, you'll get up to the front, right? Because we start pulling things off the front. So if we're not none, then, right, then I can say a new node, right, make a new node. So we'll have a new node is a node given the item. It doesn't have a next, self.node, sorry, self.node. There is no next because it's the back of the line. Then self.back, we're going to change self.back, but before we change it, we need to tell the current back, you now have someone that comes after you. Right, so self.back.next equals the new node. Then self.back equals the new node itself, right? So something comes after the previous back. Now we have a new back of the line, end of the line, front, back, and anything you want to call it here, right? Those are our two cases. So if we're empty, we have front and back. Otherwise, we're here, right? We just come after. Now, performance-wise, right? If we think about our performance, so on average time, constant, right? No matter how many items I have in my queue here, I just add a new node and point back to it. Now it's the new back. So 5 items, 5,000 items, 5 million items, still constant time performance, which is fantastic. So O of 1. Worst case, same thing. No matter how many items we have, still constant time. So we've improved our worst case performance here, adding items. We never need to do that resizing piece. That was the slow part. Now DQ gets a little tricky again as well, because if we only have one item, then front and back are the same thing. We need to make sure we're removing it and putting both front and back to none, because otherwise bad things are going to happen. So the weird case when we DQ is if front and back are the same. So to check for that, we can say, hey, if self.front equals self.back. If they're the same thing, then I only have one node here to DQ. Okay, sure, we can do that. So I'm going to take the item is my self.front.item. Right, grab the item so I can return it when I'm done. Then I'm going to set self.front is none, self.back is none, and I can return the item. Right, if we only have the one thing, if the front and the back are the same item, the same node, then get the item out of that node, front and back are now nones. Right, we're back to our empty state here. If we're not, though, right, to remove the item, again, we're going to do the same idea. Let's take this item off. So we take the 3, we save it. Right? Now, front is no longer going to point to the current front. Front will point to front's next. So we say, hey, this is no longer the front is this one. Walk that chain, walk that link, say what comes after you. Okay, great. Now, hey, good news, 5, you're the new front. So this is no longer referenced, it can get garbage collected. So we can say, hey, the item is the same idea, self front item. And then we're going to change front. So then self.front will equal self.front.next. Right? And when we're done, we return the item. Now, we can clean this up a little bit here if we really wanted to. It's doable because if we only have one item, what is front's next going to be? So once we've removed this one here, once we removed this one here, or just pretend we only had the 5 node, maybe that'll be easy. So we got rid of that node and we only have this node here. So then back is also this one, our 5 here. If we do the same step, we say, okay, grab the item, self front is self front's next. Well, what is front's next? It's nothing, it's none, right? So front would be none here. That's okay, we haven't broken anything yet, right? We say, okay, front is none now, great. So we then, if we wanted to, we could say, hey, if front is none, we should make back none. And that's doable too. So that cleans up our code a little bit here. So instead of doing all of this, I can just say, hey, grab the item, and then if self.front is none, self.back is none, equals none, right? So this is a little bit cleaner than that other version, right? Just to make this a little bit nicer for us to look at, right? It's the same process, right? And now we have less repeat code. We feel better about ourselves, right? So grab the thing that's in front. Oh, we should make sure we're not empty, right? Just, check for empty first. Sorry about that. That's an important check. So if we're not empty, we can keep doing this. Great. Grab the thing in front. Grab that item. Change front. Front becomes the next. What comes after front? If front is none, well, back, you're now none too because we're empty. That's our indicator that we're empty. And we can return that item. So performance-wise on this one, right, we have average time is O of 1. It's constant. No matter how many items we have, it's those same 4 steps, right? Make sure we're not empty. Grab the thing, change front, maybe change back, and give the item. Right? And so for worst case, same as well. O of 1. So using these linked structures is really nice for performance. Again, it takes up a little bit more memory because every time we're storing a node, we now have another thing that's in memory. And the node has to point to what the actual thing is, and then it has to track where the next thing is. So we're using up a little bit more memory here. Again, it's cheap. Memory is cheap. We have a lot of it. So and that's the trade-off we have to look at. You know, how many things are we storing here? Okay. So that is our linked queue. How about a linked deck? Right, where it's like a stack and a queue. You can add to the front, you can add to the back, you can take from the front, you can take from the back. Can we try that one? How do you think that's going to perform? Yeah, the same, because it doesn't matter how many items we have. We can just create a new node and change where things point. It's fantastic, super fast. So let's add another file here. So this is our linked deck. Again, I'll do a little copy paste here because we want the node. So our class for linked deck, we have an inner node here. We have our init. Excuse me. So again, we need to know where the front is. We need to know where the back is. Right. So self.front is none. Self.back is none. Right. And then all of the same operations here. Let me go just steal them out of here because what do we call all of them? Do we write the deck? I thought we wrote a deck. Oh yeah, pop left. Here we go. So we had append left. We had append. We had pop left, we had front, we had back. Let's come and add those in here. But again, we'll take some of these out. So I'm just going to return none to start, just to get these penciled in here. And return none. To pop left, we'll return none. To pop, we'll return none. To append, we'll return nothing here. We'll just pass on that one. We'll come back to it. And oops, all those are tabbed in wrong. To append left, we'll just pass again. There we go. Okay, so we get those lined up and we're a little nicer here. So to append to the left, we're adding a new front. right? So with our Q, we only added back, right? So when we NQ'd something, we changed the back. But this is adding to the front. We need to change the front. So similar idea. So we'll go steal our check for empty. We need our check for empty here in a minute. So to add to the left, we're going to make a new front node, right? And then that front, like we did with our stack here, right? What comes after it to add something on? It's a new node. It's whatever the front was is now the old front, right? And instead of top, it's the new item here. So we go append to the left. Let's grab this one. Oh goodness. We'll make a new node, and now what comes after it is the current front. And if we're going to append to the left, right, that's the front here. The wording here is a little funny, but I think we copied this off of the Python official deck, right? So you can't blame me for the wording. I didn't come up with it. And then we have a new front. So front is the new node. Now, we also, because we are tracking back, need to be checking here, because if we were empty and we appended left, we need to make sure we're tracking back properly, because back was going to be none. So front is okay if it's none, because that's our next. It's okay for this one to be none. But if back was none, now back needs to point to front, because we need to know where the back is. If you just have one node, you're the front of the line and the back of the line. Good news, right? So my wife and I have only been married once, like of all of our marriages. So I'm her favorite husband and her worst husband that she's ever had, right? I'm the front of the line and the back of the line. She doesn't appreciate when I point that out. So we can check, hey, if self.back is none, then self.back should equal self.front, right? In that case where we were empty, now I have one. If I wasn't empty, great, we're just going to ignore it. Back will stay the same because we added to the front. Back doesn't change here, right? A regular append, right? This is adding to the back. So this is the one we did with the regular queue. We already did this one. I'm just going to steal it, right, to NQ. No, yeah. This is a regular one here. So to append, if our front is none, we have a new front. Back is the front. If we're not empty, we have a new node. The current back's next becomes the new node. And then, hey, back, the linked deck itself, hey, you have a new back. Here's the back of your line, right? Is that new node we just created, right? So we can append, right? To pop, then popping is taking off the back here. Now, this actually gets difficult, and we're going to run into some trouble here, because to look at the back of my deck here, so let's go add, let's make a couple nodes here. So let's say we added a few here. So we had like 3, 5, and 7, right? So they're all nodes. I should have brought my tablet, I'm sorry. I had it in my hand, and I was like, no, I don't need it. Next is here. Next is here. We have the front is this one, right? And the back is this one. So the way that we're structured right now, right, because we kind of modeled this off of our queue, we know where the front is, front knows what comes next, and then what comes next, and what comes next. So if I were to just take the back off here, can I get to the thing that comes before the back? Do I have a way to say, what's the node right before the back node? We don't have that. It's not there. So I have to go to the front, go all the way across every single link until I find the one that's before the back to know which one will be the new back. So we have a problem here. So this simple structure doesn't work well with the deck, but we can fix it. It's okay. It's just code. We can change it, right? We've got that power. So let's write it like this now, and we'll know that this one is not as efficient here, and we're going to be sad about it here, right? So when we look at this one, so our, every time here is O of n, because to get to the new back, you have to start at the front and go, okay, what comes next, 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 until we get to where the next is the back, and then we stop. And that's the only way I can get the correct back. Right, so this one's bad and we're sad about it. So average is still O of n, worst is still O of n, and even best, right? and again, we don't often talk about best because I don't think it's very useful here, it's still n. No matter what, it's still going to be slow. So to do that, we have got a whole process, right? And it's okay. It won't be too bad. So we haven't done a lot of working with the links aside from, hey, what is your next? But what we can do here is we can put this in a loop, and we can keep on looping through, because we want to get from the very front node up until as many nodes as it takes until we find the node where the node's next is the back, right? Because that's where we want to stop, because we need to know what comes right before the current back to make sure that we're telling you, hey, you're the new back of the line. Right? Someone pulled out of the drive-through, you're now the back of the line. You're like, oh, this is when people behind you start driving out of the drive-through, you know you're in trouble, right? You're going to be waiting a while for that taco. So, sometimes it's worth it though. So to get there, then we need to say what the current back is, right? We know what the current back. So self back is the current back. So we need a node that we're looking at that can change. I don't want to change front, and I don't want to change back yet. So what we're going to say, hey, I have a current node is self front. So give me the front. This is the current node that I'm looking at. And then we're going to loop. We're going to say while the current node's next does not equal self.back. Right? As long as the thing that comes after you isn't the back, I need to keep on walking that chain. So to walk that chain, I'm going to say, hey, my current node equals the current node's next. So it's going to start at the front, right? Start at the front. Here's the current node, right? This one's current. Is current's next the back? No. Okay, so current becomes current's next. So now current points to this one, to this node. Again, this was a really small one here. Is the current node's next the back? Yes, it is. Our loop will stop. But if we had, 50 other nodes in here, we would just go the first node, the second node, the third node, the fourth node. Eventually, we'd get to this node where the next is the back, and we can stop. So when this loop is done, then, when current node's next does equal the back, we know we're at the item just before the back. Right? So I'm going to take my item is my self.back.item, because this is the thing we're about to return. Then I can change back, right? Because we need to say, hey, you're no longer the back of the line. You pulled out of the drive-through, right? So you're no longer the back. Good news. Current node is now the back, right? So self.back is going to equal the current node. Right? Now, we do have a little bit of trouble here, though. What's going to happen? We should actually check for empty first, right? So check for empty. But what happens if we only have one node? Right? What happens if we're in some sort of structure? Oops, I erased a little too much here. If we just had 3, and that was the back. Does the current node starts as front. Does current node's next equal the back? No, because it's none. Well, that's bad. Our program's not going to work, because we're going to try and go to the next one, and it's none, and then we're going to try and look at none's next, and it's going to crash on us. I happen to know that will happen. Usually, like as you're writing this out and you try it, it will crash on you, and you'll be really frustrated. I've got the advantage of knowing it will crash, so I'm saving you a little bit of headache here, right? And again, I'm sure you read the textbook and you saw this happening in the textbook too, right? Yes, okay, definitely. So before we do this, then we have 2 cases. If we only have one item, we do a special thing. Otherwise, we can do whatever, right? So if self.front is equal to self.back, we do the special case, right? Well, this one's pretty easy then, right? I have the item is self.front.item, and then self.front equals none, self.back equals none, and we can return the item. Right? If you only have one thing, take that thing, front and back are now none, we're empty, return it. Now, if you put a return here, you don't need an else, right? It just becomes redundant at that point, because return will stop your function. That's why I'm not having the else here, just to, saves a little bit of tabbing. Otherwise, this process will work for us, and we'll have to walk those chains, walk those links, what's next, what's next, what's next, what's next, what's next, what's next, do the really slow thing here, right? So this one's bad. Pop left is going to be great, because our links go what comes after me, starting at the front. This one's really easy. This is the same thing as our Q, Dec, or DQ. It looks like they're spelled the same way. So sad. So to pop left, it's just getting rid of the front item. Make sure we're not empty. Grab the front thing. Front becomes the front's next. And then our special case, check, are we empty now? Right? Because this is important. Set back to none. Return the item. Right? Getting the front item, sure, really easy. Actually, we can just return the item, right? We just say return here, save a line, right? Check for empty. If we're not empty, give them the front. Back, right? Sure, check for empty. If we're not empty, give them back's item. Right, so front and back, again, these are fast. We just are looking. We don't need to do any sort of work. So these are perform really quick here, right? Top left, this one's fast, right? There is no walking. We don't have to walk every single link to change what is the front is, right? So this performance is okay, right? So our average case, O of 1, worst case, O of 1, right? So the only issue we have here is pop. Pop's our sticking point because the way that our nodes are working, when we're pointing front to back, this one's slow, right? Remember, the stack works the other way around. The stack says what's underneath me. It's not what comes after me. It's really what was before me. So if you imagine, if we took that stack and kind of laid it down, the first item, the second item, the third item, the fourth item, they point to what comes before them, not what comes after them. I know I called it next because next is easier. Just otherwise we have to change our terms every time. But that's why this linked stack is fast, because it knows what comes before it, not what comes after it. We're just using bad words here, and I apologize. Right? This is really what comes before it or under it. Right? Before or under, does that make sense? Why I'm calling it that way? Okay, cool. So can we make this faster? It's just code, right? We get to write it. What would make it faster? What was the slow part about being able to change the back? Right? What was our big problem that we had? We had all these nodes. We had 3, 5, and 7. Right? Why was it so slow? Right? We had no way of knowing what comes before the back, right? Could we change that? Yeah, it's just code, right? So what if nodes also knew what came before them? What if nodes had a previous, and you would point to what comes before you? Could we do that? So the front would have nothing that comes before it. The back has nothing that comes after it, but all the nodes would know what comes before and after. Hey, this comes after me, this comes before me, so we can go either direction. That's called a doubly linked node, because it has two links, right? It has a previous and it has a next. We could do doubly linked nodes, and that would solve our problem with removing from the back, because we can say, hey, back, what comes before you? And it would know, because it has that link here. Now, this means we're storing even more memory, though. We're using more memory. Using more memory, because each node now has the item that it's pointing to, it has a next, and it has a previous. So we're increasing our memory usage, so that the space complexity increases here. But what we're gaining is now I can take the back item off in constant time, because I have all my links. So again, it's a trade-off, right? If we want to use that deck structure, because we want to be able to add to the front, add to the back, either way around, right? That kind of combined stack and queue. If that's how our structure is, and that's what we need to do, this will give us better performance. Okay, so I'm going to leave this one. I'm going to call this singly linked deck here, with the note that this one is slow, right? And then we'll make another one for the doubly linked deck. And it's okay if this hurts your head. Dealing with these links and objects, it's a very new concept. We haven't really done anything like this before. Right? We've never said, hey, this thing points to the next thing, and that next has a next, and that next has a next, and that next has a next. It's a very new way of thinking about how we store data. Okay, so we'll take a little bit of time. We'll play with it in lab. We'll have some fun with it, adding things, removing things, and we'll have some fun on Tuesday with that. So I'm going to add another here. This is our, that was a new, sorry, I thought I clicked the wrong button. A new doubly linked deck. Okay, now a bunch of things are going to change here, and that's okay. But the first thing that's going to change is our node. Right? If node needs to know what comes before it, we're going to add a self.previous. Some people like just prev here. Again, I'm not a fan of abbreviation, so I'm going to say self.previous. It'll look different in the book, but that's okay. We'll equal the previous. So next is none, and previous is none. Right? Unless you tell me otherwise, I'm going to assume you don't have one. just like next was. If you don't tell me what comes after you, you don't have anything after you. If you don't tell me what comes before you, you don't have anything that comes before you. So self and back are still none to start. To append to the left, right? That's appending to the front, right? The front of our queue. Do we have anything that comes before us or for the front of the queue? No. So we don't even need to add the previous here. Same thing. This just works, right? We're okay here. To add to the back now. Now we have something, right? If we're adding to the back, we need to know what the current back was, right? Well, the front was none, then there is nothing. It's only going to be a single node. It will have nothing that comes before it, right? It'll be none. So this case is okay because we want nothing comes before, nothing comes after. But if we had something already there, we now have a new previous. We don't have a next, right? Because we're the back of the line. There's no one after us. But before us, we need to know who used to be the back. So we can say, and this is where Python is fantastic, right? We can use these named arguments. I can say, hey, the previous is self.back. Remember, you can use named arguments here to match with these optional default parameters. Otherwise, you'd have to say none and then self back. So you know the other way of doing that. New node is self.node given item none and self.back, right? We could do it this way and use the positional arguments where the position, the second item here is none and then self.back. So I much prefer using the named arguments here is all. So I'll just leave that commented out. Okay, cool. So now we know what comes before us. We have our previous. That's it, right? So appending to the left, appending to the back. That's all we had to change, right? But now when we start removing things here, we don't need to do any of this. Our pop now, we get to say, yay, these go back to constant time. Because we don't need to check for any of this crazy stuff. Where we don't have to do the walking here. So same idea. If we are only a single node, we only have a single node here, front to back become none. But now we don't have to do any of the walking here. So my item can be the self-back item, right? And then self.back can change to self.back.previous here, right? Say, hey, you're no longer the back now. Back is what comes before you. Back now points to this one. Now, what's going to happen though? If we still have this node here, it's still being pointed to. The current back thinks it has a next, right? This node here that stores the value 5, it still thinks it has a next thing. That's bad, right? We don't want that. We need to break this link so it can get garbage collected. That's really important. So self-backs becomes self-backs previous, and then self.back.next is now none, right? You don't have anything that comes after you now because you're none. Right? You are the back of the line. No one is after you. So this is an important addition here to make sure we are getting rid of all the references to the old back. Okay, popping from the left, right? Front becomes front's next. But now what happens to the link that it had, right? We need to do some cleanup. So if I remove this front node here, 3, and now I say, hey, front, you're no longer pointing at the 3, you're pointing at this one. What do we have to clean up? We have to clean up that previous link, right? The new front needs to know nothing comes before it to make sure it can get garbage collected. So after we do that then, right? And if it is none, we can't do that, right? So now the special handling here is going to be interesting. So we take front becomes front's next. That might be none. There might have been nothing next. So if it is none, back becomes none. Otherwise, if it's not none, then I can say self.front.previous is none, right? If I don't have this check here, and I try and say self.front, and self.front is none, and I say a none.previous, it's going to crash on me, right? Python will say, you can't do this on a none, right? You can't, there is no previous attribute on none, and we crash. Again, sometimes it's nice to see those things crashing, and I feel a little bad we're skipping it. I'm sorry. Like as you build it and it breaks, you can think about it for a minute, but we're saving a little bit of time here, right? We're a little short on time. That makes sense? So we do a little extra cleanup here now, and we say, hey, to make sure that as the front and back change, those previous and next values are correct. Because if you're the back of the line, nothing's after you. You have no next. If you're the front of the line, nothing comes before you. There is no previous. Okay, front works the same, back works the same, check for empty works the same. You should be in pretty good shape. Now, what we haven't done yet is try it. Oh, I'm sorry, I got to change the name of this class too. This is the doubly linked deck. We haven't actually tried it. So I think it's going to work, right? But we should probably test it out, right? Should we write some tests? Yes, of course you want to write unit tests, right? We love unit tests. So let's go add some unit tests. Let's go add some tests. Oops, oh my goodness, I missed it. Go to test. Make some new tests. Let's see, we want to test all of them, right? Make sure they all work. Test for empty or check for empty. We can test as part of testing some of these other things. We don't generally test private helper functions, right? Because they're used in the public functions we're testing, right? So we don't necessarily test them directly here. All right. So to append left, all right, let's go from doubly linked deck, import doubly linked deck, append left. So we're going to arrange, we're going to act, we're going to assert. Right? What do we want to set up here? So to append left and make sure that it works, maybe we want to add 2 or 3 things and then make sure we can pull off 2 or 3 things in order. Right? Again, there's lots of different ways we can go about testing this. We're going to look at, are we going to get every path running? Are we going to get 100% code coverage? So make sure that at some point back was none. Well, that was easy. When it's empty, back is none. This one will run. So really just a single test of this will exercise 100% of the code. But are we going to feel good about it? Maybe not. Maybe we want to try adding 2 or 3 nodes, right? 2 or 3 items, and then make sure we can get 2 or 3 items back out. In terms of code coverage, it's still the same, but are we going to have a good feel for whether or not it works? We definitely want to add more than 1, at least. Right. So let's go test that one. So let's say maybe the first value should be what, 5, and then the second value should be 7, right? And then we need a doubly linked queue. So we'll make our, we'll just call this our deck here. So we'll call this our deck. It's a doubly linked deck, right? Init doesn't need anything. We're not testing the init method here, so it's not part of act. Now, act is where we're going to call append left. So if we want the second value to be 7, we need to add that one first, right? Because we're appending to the front. So if I put in the second value and then I add to the front or append to the left 5, I should have 5 and then 7, right? So we just have to put them in kind of a backwards order here. So we'll say, hey, my deck, I want to append left my second value, and then deck, I want to append left my first value. Right? So if I put them into that order, the 7 goes into the first thing, and then we're going to say, hey, there's a new front, here's the 5. So first and second. Right? Now we've got a couple options. Right? We're not really testing the popping yet here. So if I just want to say, hey, what's the front and what's the back? We could do that, right? Because front should be 5, back should be 7, if we've done this right. So we can get an actual front then, or actual first is going to be my deck.first, or front, and an actual second is going to be deck.back, right? Again, if we added 3 or 4 items, it'd be a little different, but we're just testing. We just add 2 items, make sure that the front properly stays at the front, right, and the back is the back. I think this should work out pretty well. And then we'll assert equal, right, my first value and the actual first, and we'll assert equal the second value and the actual second. Let's give our test a run. If it works, I'm going to be really happy. Oh, it failed. Okay, that's okay. That's okay. All right, so we have a problem, and this is why we test. So it says, hey, none object is not callable. Deck.front. Why is deck none? Okay, sure. So saying in my test at line 14, actual first, deck.front. I'm real confused. None objects not callable. All right, let's put a breakpoint in and let's try and debug our test and see what's breaking. All right, so we have our deck here. Our deck is a doubly linked deck here. It has a node. So node is the definition for node here, right? We have the back, we have the front. So the front node has a 5. Its previous is none. It's good. It has a next. The next is another node. Its next here is a 7. Its next is none. Its previous. 7 has previous is none. Well, that's not good. So something didn't work right when we appended. Let's take a look. So as we're appending left here, we said this is what our next is. Oh, so when we went and added this here, this is good. So let's draw this out. Our first one was okay, right? We added a 5. Oops, we need more bars here for previous and next. It had none previous, none next. It was the front and the back, right? When we went to go append, I'm sorry, we did the, was it 7 or 5? We did the 7 first, sorry, so 7 was first. So 7 here. We added the 7 because we did this one first. And we said, okay, let's add a new front. So our code here for adding to the appending left said, okay, let's make a new node. Its next is the current front. So we made a new node here with the value of 5. We said, hey, your next is currently front. That's this one here. And then we said, okay, hey, front, you're the new node. Sure. So front now points to the new node. What happened to the previous front's previous value? We never changed it, right? We never did that cleanup. We didn't need to tell it, hey, there's something that comes before you now, right? Okay, we can do that. So a couple options. Lots of different, some people love doing this like in one line. I'm not the biggest fan of that here. So I'll show you that, but I'm going to show you that it's kind of ugly. So instead of doing this one here and this one here, we could say, oh, sorry, not those ones. We could say self.front.previous equals a new node, self.node. And we could set front's previous that way. I think this is a little ugly, but like we're saying, hey, directly setting previous to this new node, we could do that. Not the prettiest thing, and then if front is none, we still have trouble here. So this is not necessarily ideal here to go about this way. Not that great to go about this road. So we'll set the new node here. Then we need to say, before we change front, right, if self.front is not none, right, because we could have been empty. If we were empty, front is none, it will crash on me here. But if we're not none, then self.front.previous is the new node, right? And we can fix this link here. We can say, okay, hey, current front, this was before we changed front here. We added the new node knows what comes next. Front is here. We said front previous, you're now the new node, right? And we erase this none here. Then we change front to be here, right? So we're going to make sure we're adding in that link here for us, which is nice. So that should do some cleanup here, and I think that'll take care of our test. Let's give it a shot. Oh, no, it still failed. Okay, all right. So none is still not callable. Well, let's go and debug it again here. So we have our deck. Right? We have the front. The front is a 5. That's correct. It has a next. Its next is 7. 7 has a previous. Previous is 5. 5 has a next. So as you're like looking through the debugger, this is just an infinite loop, right? Because they point to each other, point to each other, point to each other. So looking through that's not too helpful. And then how about back here? Back is 7. It has a previous. Previous is 5. Great. That one looks okay. So let's step into our code and see what's going on here with deck front. What? Node object is not callable. My node object. Okay, node object. It's not a node. Deck.front. Is our method not defined right? Front? Why is it not deck.front? Front. Oh, so I did a bad thing here. I'm sorry. we have a function named front. We have an attribute named front. We confused Python. All right, so that was bad here. So let's go and change these here. So that should not look like that. So again, I don't want to have to do a lot of work here. So I'm going to right click and go refactor rename, and we'll just say this is private front. And they should probably be private anyway, because we don't want people accessing these directly. That was my mistake here. We'll rename back as well, because that's better. Okay, now we should be in better shape here. One more time, we'll try our test. Uh-oh. Node object not callable. Again? Okay, it must have changed the wrong thing we refactor renamed. That's okay. Front? Back? Oh, it refactored it here. That's weird. Okay, I didn't look at the refactor close enough here. That was why. So we have to call the front function, not the front attribute. One more try. One more try. Hey, it passed. Okay. This was good. This is debugging. So we can add two items. When we add them to the front, they seem like they added in the right order. Seemed okay. Let's try adding to the back then. Right, same idea. If we add to the back here, we put them in first and then second because we're adding to the back. Right, so we want to actually append the first value first, then we append the second value. Right. If I add my 5 to the front, I'm sorry, if I add my 5 to the back, it's the front. I add my 7, it's now the back. I have a front and a back. Should be the same ones here. Let's give that one a try. And that one passed. All right, we're 2 for 2 now. This is good. Pop and pop left. So to do that, when we're actually removing items, we probably want to remove more than one, right? To make sure that all of the links are there and not breaking. Right? We could just remove one, but again, as we look at our code coverage, we go remove these things. Two different cases, so we want to make sure we get to an empty state, so this one runs, and we want to make sure that the other stuff runs too. So if we add two things and we pop them both off, we should get back to that empty state. We should be feeling pretty good, right? So let's try it. So we'll go add two items. Oops. Right, this one adds two items. So again, either way, if you want to append or append left, we've tested that one already. We have to use it here, but it's not really what we're acting on. So I'm just going to move that up to the arrange section because I want to just add two values, right? Then what we're actually doing then is we're going to pop them off. So the actual first should be, if we're popping, let's see. So the first would be the second would be the first one that we pop, right? Because if we're popping from the end of the deck, the second thing we added should be the back. That'll be the first thing that gets popped off, right? So if we add two values, we add our 7 and our 5, we pop off the back, it should be the 7. So that'll be the second item we added. And then my actual first then should be my deck.pop again, right? And those should match. Let's give that a shot. Uh-oh, that one failed. None is not 7. Okay, so we have an issue here. So when I got my second value here, we did not get the 7. Let's take a look and see. So let's put it in debug mode and debug it. All right, so we have our deck. We have back and front. Front is 5, 5. Next is 7. So it looks like we're in the right structure. Right, structure was working fine for us. So let's check out what happens in pop. So let's step into our code. We're going to check for empty. We're not empty. Does front equal back? No, front doesn't equal back. Okay, so let's grab the back's item. So we have 7. Oh, I missed a return statement here. We grabbed the item, we never did anything with it. We never returned it. That's my bad. So we got a return item. Okay, that might be it. Let's give that a shot. Right, and it was telling me to. I didn't even notice. I noticed it was grayed out. This local variable is never used. Oops. Return. All right, let's try that. Hey, all right, it passed. Okay, so one bug. Right, we found it. Awesome. How about pop left? Same idea. Let's go grab our values. Now, when we pop from the left, the first thing we added should be the first thing that's popped left, right? So if we pop left, should be the first thing. Then if we pop left again, that should be the second thing, right? Because if we have 5 and then we add 7, we're adding to the end, we're appending. Popping from the left should be the 5 for the first thing. Popping from the left again should be the 7, should be the last thing. So let's give that a shot. All right, now I'm passed. Feeling all right so far. Testing front and testing back, we've actually used those in our other tests, right? Because we didn't have ways of accessing those values directly. We used those public functions. So these have already been tested, right? We don't need separate tests for them necessarily because we used those as part of these other tests. And I feel okay with that because that's how we go get the front and back values, right? And we wanted to check what our front and back values were. So I feel pretty good about our doubly linked deck. Now, what we haven't done here, and just we have 100% code coverage, but we haven't gotten to the point where we filled it, emptied it, and then refilled it, right? Because we have these cases where we said, hey, if we become empty, my front and back should be none. I think it's going to work, right? I know this code ran, but did it do what I expected it to do? So maybe we want to add an item, take an item off, add an item, make sure that it still works. Just something else we can test, right? More tests are good. Do we need it? Maybe not, but do I want to make sure that what I think it's supposed to do works? Yeah, right? Because any code that's worth writing is worth testing. So we're going to test add, empty, add again. Sure, maybe that makes some sense. I don't know. So I'm going to add the first value here. Let's see. Let's do this in ACT because this is really what we're testing. We're going to append the first value, and then we're going to pop the first value off. And then we're going to append the second value, and then we're going to pop that value off. Again, pop left, pop. It shouldn't matter because there's only one, right? Should be okay. So if we put something in, take it out, we should be able to put something in again. Right? And then, let's we could check here. I guess we pop it back off. We're going to be empty again, but we could check for front and back values. I think we did that already. So let's try this one here. I think that'll work. And that one passes. Okay. So we added, we emptied it, we added it again. Life was good. Now what we haven't tested yet is the assert, or the error for empty, or check for empty, right? And there's a specific syntax for it that I can never remember. So we'll do this one in lab. I'll double check what that is for you. You do like a with. I always forget what it is. We could Google it here, but we're almost out of time here. That sound okay? All right, awesome. So we'll play with these in lab. What we want to do is look at, can we use these in particular solutions? When would it be useful to have a deck? And we'll play with the deck and use it in a solution. A drive-through is pretty good for that sort of thing. Because you can add to the back. Sometimes people drive off, so you need to take them off as they drive off, that sort of thing. We'll pretend like people never drive off from the middle. Because usually, like, once people have gotten behind you, you're committed. But if you're the back of the line, you're like, oh, this is taking forever. You might drive off in the back of the line. So we might have a little bit of fun with that. Okay? That sound good? And we're still working on the recursion project. We've got that one coming up due next week, right? Okay? So bring your questions for that, and we can go from there. For the recursion project? So you could do them as a unit test, or just in a main if you want to do that. That's okay too. I like unit tests. I'm a fan of that. I don't think there were any points for it there, right? Let's double check. Because the rubric had just... I didn't add a rubric for you? Oh my goodness, I'm sorry. I thought I added the rubric. Let's do that. So for our points here, this is our checkers. And we're going to use this for grading. So let's have our class accepts a checkers board of a 2D list. So just having the right structure here for that class, right? That we can have our checkers solver, or I guess checkers solver, whatever class we're going to call this, right? We'll accept the board. So given any checkers board, right, we'll go do that. And then the init verifies the board is valid. Verifies, come on, spelling. There we go. 2 points, making sure the board is in a valid state. Right, we said 8 by 8, all the pieces have to be on the same color square, right? Whether or not they're all white squares or black squares. right? Because otherwise you can't really play checkers, right? Because the diagonals won't work that way. So 2 points for validating, right? Yeah, ensure raise an exception, right? And then we're gonna have confine number of jumps for a single checker piece, a white checker piece. Get 2 more points there, and then find the maximum number of jumps for all white checkers. 4 points. So if you just can do it for one, 2 points there, right? But actually being able to do it for checking all of the white checkers and finding what the maximum number of jumps was, 4 points there. Okay, so again, we're kind of building it step by step by step. So make sure you can take the board, then make sure you can validate the board, then make sure you can do it for one checker piece, then make sure you do it for all checker pieces and find that max value, right? That make sense? Yeah. So if I give you a 2D list, you need to make sure it's in the form of a valid checkers board. So it's an 8x8 with all the pieces being on the same color square. So when we look at like a checkers board, not checks board, checker board, right? All the pieces will be on the black squares here, or all the pieces will be on the white squares here. So I don't know, I don't actually recall, I don't think it matters one way or the other actually to the game of checkers. But as long as they're on the same color square, then they'll be in diagonals. Because if you mix and match, then like if you have a piece on this square and this square, there's no diagonal jump, right? Because all the jumping in checkers happens with diagonals. So you have to be on the same color for that to work, right? So if you have a white piece here, do they have any other like set up further? This one here, sure. So, I don't think there's any jumps here, but they're all possible diagonal moves here, right? Places we could go. So right now, the only jump that could happen is this white checker could jump to here, right? This checker has no jumps, this checker has no jumps, this checker has no jumps, this one has no jumps, this has no jumps, this has no jumps, this has no jumps, this one has a jump. So our maximum number of jumps would be 1 here, right? Does that make sense? Okay.
When we make the jumps, do you want us to like pick up the checker?
Yeah. Yeah, if you don't pick up the checker, you're just gonna jump back the other direction. And then you'll jump back and you'll jump back and you'll jump back and you'll be like, I have a zillion jumps, and you'll be really confused. Yeah. Yeah, so that's part of that process. You change the board, and then when you come back from that backtracking recursion step, you undo that change, like we did with the maze solver. Pick that breadcrumb back up. Right? We tried it, didn't work. We're done with it. Pick it back up. Okay? Good questions. Awesome. So you folks take care. I will see you on Tuesday for lab, and then we'll move on to the linked lists, which gets to be a lot more fun, where we pretend to be a list. We can get stuff by index. All right? See you around.